All right, hello everyone, and welcome to Unit 6, Lesson 4, which is on heat capacity and calorimetry. Today we are focusing on calculating heat absorbed or released in a system based on amount of substance, the heat capacity, and change in temperature. Your essential knowledge is that the amount of heat transferred between two bodies may be quantified by the heat transfer equation, which is Q equals mcat. Calorimetry experiments are used to measure the transfer of heat. So the calorimetry experiment is going to give you delta T. The first law of thermodynamics states that energy is conserved in chemical and physical processes, and the transfer of a given amount of thermal energy will not produce the same temperature change in equal masses of matter with differing specific heat capacities. Calorimetry is a method that we use to study how heat moves between a system and its surroundings. Because we cannot directly measure the total enthalpy of a system, we instead measure changes in enthalpy by tracking changes in temperature during that exchange, and that's going to be denoted by delta H. This is possible because when heat is gained or lost by a substance, its temperature changes in a predictable way. When we quantify this relationship using the equation Q equals mcat, Q is going to represent heat energy transferred, M is our mass of the substance in grams, C is the specific heat capacity, and delta T is the change in temperature either in Celsius or Kelvin. Specific heat capacity tells us how much energy is required to raise the temperature of 1 kilogram of substance by 1 degree Celsius, and it varies depending on the material. So metals have low specific heat capacities because they heat up very easily, while substances like water have high heat capacities because they require much more energy to change the temperature. In calorimetry, we study heat flow by allowing a reaction to occur in a controlled vessel, and then we measure how the temperature changes. Most calorimeters are going to use water as its liquid because it has a high specific heat and it also absorbs and releases heat in a predictable way. In a bomb calorimeter, the reaction takes place inside a sealed container surrounded by water. Any heat released by the reaction increases the temperature of the water, allowing us to determine heat change under constant volume conditions. A constant pressure calorimeter is an open system. That means the reaction occurs in a solution while exposed to the atmosphere, so pressure is going to remain constant, and we track the temperature change of the reaction itself. And then a coffee calorimeter is a simple version of that using insulated styrofoam cups. That's going to reduce the heat loss to the surroundings while measuring the temperature change of water during the reaction. In all cases, temperature change is the key measurement that allows us to calculate how much heat was absorbed or released, which is Q. So a coffee cup calorimeter is designed to measure heat flow by keeping the reaction as insulated as possible from its surroundings. Its main parts include a thermometer to measure temperature change, the reaction mixture where the chemical or physical process is going to occur, and a stirrer to keep the mixture moving so the temperature is uniform throughout all of the liquid. The reaction is held inside the insulated styrofoam cups. Those are usually nested together, which is going to minimize heat loss. And then a heat-proof lid or stopper is going to sit on top to reduce heat exchange with the air. The goal of this setup is to create a nearly isolated system so that most of the heat gained or lost comes from the reaction itself rather than the surroundings. The better the insulation you have, the more accurate your heat change of the reaction is using a thermometer. So the first law of thermodynamics tells us that energy is conserved. It cannot be created or destroyed, only transferred or converted from one form to another. So in the context of calorimetry, this means that in a closed system, the total amount of energy stays constant, even though the form of that energy may change. So in a calorimeter, we mainly track heat transfer, and the first law of thermodynamics helps us understand that any heat lost by the reaction must be gained by the surroundings and vice versa. So energy is always balanced. So in our calculations of Q equals MCAT, we have C, which stands for specific heat. Specific heat tells us how much energy is required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Substances with high specific heat require a lot of energy to warm up, while substances with low specific heat heat up quickly with relatively little energy. This explains everyday experiences like why it takes long for water to boil, because water has a very high specific heat at 4.184, meaning it absorbs large amounts of heat before its temperature rises. In contrast to that, materials like sand have a much lower specific heat, so they gain temperature rapidly in the sun, which is why beach sand can burn your feet even when the ocean water feels kind of cool. So in years past, I have students get confused on the positive and negative sign in calculating Q. If you would rather, when calculating Q, you can just forget positives and negatives, solve for Q, and then at the end, just think, okay, if I went down in temperature, that means the reaction is endothermic, or energy was put into the system, which means Q has to be positive. If the temperature of the water went up, then the reaction was exothermic because energy was released, and Q must be negative. So you can do it that way, or you can just make sure you calculate delta T correctly, which is final minus initial, and then you'll get the correct answer as well. All right, let's do a few examples. So this one says an insulated cup contains 255 grams of water, and the temperature changes from 25.2 degrees Celsius to 90.5 degrees Celsius. Calculate the amount of heat released by the system. The specific heat capacity of water is 4.184. So this one says calculate the amount of heat released by the system, which means they're already implying the sign in the question. So all you're giving me is the amount of energy, and that can be either in joules or kilojoules. So since we are calculating amount of heat released, I know we are solving for Q. We know Q equals mc delta T. M is in mass, so grams. That will be 255. Specific heat of water is 4.184. And then our change in temperature would be the difference between 90.5 and 25.2, which is 65.3 degrees Celsius. So you can see our degrees Celsius is gone and our grams is gone, so we're left with joules. And when we solve for that, we end up getting 69,700 joules, which is also equal to 69.7 kilojoules. And AP Chemistry would have accepted either of those answers. All right, so this next one says a student investigates the enthalpy of solution, which is delta H, for two alkali metal halides, LiCl and NaCl. In addition to the salts, the student has access to a calorimeter, a balance with a precision of plus or minus 0.1 grams, and a thermometer with a precision of plus or minus 0.1 degrees Celsius. Part A says to measure delta H for LiCl, the student adds 100 grams of water initially at 50 degrees Celsius to a calorimeter and adds 10 grams of lithium chloride, stirring to dissolve. After the lithium chloride dissolves completely, the maximum temperature reached by the solution is 35.6 degrees Celsius. Calculate the magnitude of heat absorbed by the solution during the dissolution process, assuming that the specific heat capacity of the solution is 4.18. Include units with your answer. So this question specifically is saying calculate the magnitude of heat absorbed. So same concept, I'm solving for Q. Absorbed is already implied, so all I'm doing is giving you the amount of energy. You do not need to put the plus or the minus in the question. So we are solving for Q. I am given my mass, which is a total of 110 grams. And that's because we have 100 grams of water and 10 grams of lithium chloride. And then my specific heat is going to be for the solvent, which is water, and that is 4.18. And then my change in temperature is from 50 degrees Celsius to 35.6 degrees Celsius, which is 20.6 degrees Celsius. We can see that we are only left with joules, and that's going to give me 9,470 joules. You could also answer it in kilojoules, which would be 9.47. And here is the actual mark scheme given by AP Chemistry. So here we have our values that we just calculated together, and you can see that 1 point was earned for the correct setup, which is just plugging in to Q equals MCAT, and then 1 point was earned for the correct answer with correct units. And you can see that you could have either answered in joules or kilojoules. It did not specifically say what units it wanted it in, so either way would have worked. All right, and for our last example for today, it says calculate the magnitude of heat energy in kilojoules absorbed by the water. So we want it specifically in kilojoules, and again, absorbed is already implied, so we don't need any signs. We're just looking for our value in kilojoules. So let's look at our experiment setup that we have here. We see that our propanol is down here in this container that we are lighting with a wick, and that is what is heating up the water. Now remember, in the last example, the lithium chloride was dissolved in the sample of water, so we include both of those masses together in our calculations for heat absorbed or released. In this case, our sample of propanol that is being burned here to heat up the water is not in the sample of water, which means we are not including that in our calculations for Q. So now that we know that, let's go ahead and calculate Q, or the heat energy that is absorbed by the water. So for this specific question, again, we only have the mass of water, which is 125 grams. Then we have the specific heat of water, which is 4.18. And then we have our change in temperature, which is going from 22 to 51.1. So that's going to be 29.1 degrees Celsius. And then we can go ahead and solve for Q. So that is going to give us a value of 1.52 times 10 to the 4th joules. However, it wanted that in kilojoules, so we're going to divide that by 1,000. So our final answer is 15.2 kilojoules. And I apologize for my dog snoring in the background. And here is our mark scheme for this question.